today we are going to learn chapter 2 of the textbook. The title is Proofs. So today we are going to learn various techniques to prove propositions. Alright, so let's begin. The first section, 2.1, mathematical systems, direct proofs, and counterexample. So yeah, we're gonna introduce various terminology. Can you read this? What is this? Mathematical is this visible? Okay. Maybe it's too thin. A mathematical system is what? Consists of axioms, definitions, and undefined terms. So this is the definition of a mathematical system. This is what a mathematical system is. It has axioms, definitions, and undefined terms. So what are those? Axioms. Axioms are statements or propositions that are assumed to be true. So in order to do mathematics, we need a mathematical system, and for that, we need axioms and definitions. Because we can do something when there are something already exists. We cannot do anything if there is nothing. Definition. So axiom is a definition or definition. I don't know. What are definitions? Definitions are used to create new concepts in terms of existing ones, let's say. Existing ones. So by introducing or defining definitions, we can enlarge our language. We can create more and more concepts by using definitions. What are undefined terms? So we cannot we cannot define everything. Because if you define something, you need to define this using existing ones. So then you can ask, what is the definition of this? And if you want to define this, you need to use another existing ones. So if you go on and on, you'll never finish. So we need to have at least one or several terms that are defined without definition. So undefined terms. But these will be some kind of concepts that are quite obvious in our intuitions. But we cannot really define mathematically everything. Are used to not this one. Are implicitly defined in the axioms. So it should be clear the meaning So these are the things that consist of mathematical system. Okay, so in a mathematical system, we will derive many statements which are true, and they are called theorems. So a theorem is a proposition that has been proved. Proved to be true. So axioms are statements that are assumed to be true. So we don't prove axioms, they are just assumed. But theorems, they can be proved. After proving the truth of a theorem, we can, of a statement or proposition, we can say that it's a theorem. And in math, if you look at math, a textbook in math, you will see theorem very often, and also lemma. Lemma is basically a theorem. It is a theorem that usually used to prove another theorem. That is used to prove another theorem. It is a theorem, but kind of a step in between to prove another one, another theorem. Let's write theorem this way, THM. And a corollary is also a theorem, but that say follows easily from another theorem, let's say. So once you have a theorem, there can be several corollaries. Corollary means it's a theorem, but very easy to prove from the existing theorem. So in Korean, people say 정리 for theorem, lemma is called 보조 정리, corollary is called 따름 정리. But these sentences mean that thing. So a proof is an argument that establishes the truth of a theorem. So once you have a proof of a theorem, finally it becomes a theorem. Before any proof, it's just a conjecture or just a proposition that we don't really know whether it's true or not. But once you have a proof, it really becomes a theorem. Okay, so we will use this in mathematics. We use this in mathematics. Yeah. So I'm going to give you an example of a mathematical system in the next page. Okay? So example, Euclidean geometry. So in order to be a mathematical system, we need some axioms. So let's see axioms of Euclidean geometry. So given say two distinct points, there is exactly one line passing through the points. So in a diagram or figure, suppose that you have two distinct points in a plane or in this space. There is exactly one line passing through this. This is an axiom. We don't prove this. This is an axiom in Euclidean geometry. Another one, given a line and a point outside a given line, there is exactly one line through the point parallel to what's this? Parallel to the given line. What does that mean? So we have one line like that and a point outside of this line. Then we must have exactly one line through this point and parallel to this line. Okay, yeah, these are the axioms. Here, what are these? Point and line. These are undefined terms. Here, point and line. These are undefined terms. We don't define this, but we have the intuition to understand this. Yeah, people. So how can we define a point? Sometimes people say it's something that has no width, no nothing, or just. Yeah, if you think about this, it's quite difficult to define this. But we all understand what a point is, so we just go without definition. It's an undefined term. Same for the line. Right, but we can define many things. So here are examples of definitions. So the axioms definitions. A right triangle is a triangle one of which angles is equal to 90 degrees. So it's a right triangle like this. So we defined a right triangle using existing terms like triangle. So we need to define triangle first, but yeah, let's assume that triangle is already defined. Triangle is something that has 3 points and sides like that. And right triangle can be defined this way. Yeah, actually there are many, like a lot of definitions in Euclidean geometry. I'm just listing just two. Two triangles are congruent, are said to be congruent if their vertices can be paired such that corresponding angles are equal. Angles and size are equal. So like, I don't know. So suppose we have A, B, C, X, Y, Z. Then we can pair, meaning you'd give kind of one-to-one correspondence between the vertices. So okay, A matches with Y, say C matches with Z. So we can pair this like 3. Then their corresponding angles. So this angle is equal to this angle. This angle is equal to this angle. This angle is equal to this angle. And the corresponding size, these have the same length. These two have the same length, etc. So this is a definition. If you have this definition, you can determine whether two given triangles are congruent or not. So in this mathematical system, you can define whatever you want. You can define very strange definition. But usually we use definitions which are useful to do something. These definitions are not random, not taken random. They need, so mathematicians, they needed this kind of definition to solve some problems they wanted to solve. So in this way, by making more and more definitions and more systems, you can more and more theorems you can build, you can enlarge your math system. That's what mathematicians do. Okay, theorem. Let me tell you one theorem. There are many, of course, many theorems in Euclidean geometry. The sum of the angles of a triangle, let me just try, angle is 180 degree. This is a theorem. Theorem means you can prove this using just axioms and definitions and existing theorems. So theorem is like this, and corollary to this theorem is something like every angle of a regular triangle is 60 degree. Yeah, easy theorem. This is a theorem which is derived from this theorem very quickly, right? Because we know that the sum of these angles are 180. There are three angles. Regular triangle means the angles are all equal. So each angle must be 180 divided by 3, so 60. The corollary is something like this. Very easy consequence of a theorem, but still useful to do something else or by in its own. Any question? Okay. Okay, what about lemma? I didn't tell you about lemma yet. So, example of a lemma. So let's use another. It's not in Euclidean geometry system, but yeah, in general math. For every positive integer n, either n minus 1 is a positive integer or n minus 1 equals 0. Yeah, which is quite obvious. You can prove this very easily. So it's a theorem. We can prove this using just the definitions and properties of positive integers. But it's a lemma because usually a lemma is not very interesting in its own. So if you look at this, it doesn't really look very interesting. But it can be used to prove another theorem. Although it's very simple, you can use this to prove something. But in fact, determining whether this is a lemma or corollary or theorem is completely subjective. It's not. So some people say this is very interesting and it should be called a theorem. That's fine. It's up to you. But if you want to use this to prove something, you can call it lemma. So deciding whether this is a lemma, corollary, theorem, this is personal. Can be a personal preference. All right. So we cannot have a exam problems like, is this a theorem or theorem or a lemma? That's not a math problem at all. All right? Question? Is it clear? Do you think this is a lemma or a theorem? If you think it's a theorem, it's okay. It's up to you. All right, direct proofs. So now we want to talk about proofs. So there are several proofs, direct proof or indirect proofs, of course. So I told you a proof is an argument to prove a theorem. So once you have a proof, you can say that, oh, now this is a theorem. This is true. So a theorem looks like this. Usually, a theorem is usually of this form. For all x1 dot 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 xn, if p of x1 dot 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 xn, then q of x1 dot 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 xn. So a theorem usually writes in this way. For all, so we have specify what these are for all, or for some. If we have some assumption, if p, then we have conclusion. Theorem usually looks like this. So, example. This is a very famous theorem called Pythagorean Theorem, or Pythagoras Theorem if you want. For every triangle, say ABC, if the angle of C is equal to 90 degrees, then this is a right triangle, then the length, side length AB squared equals AC squared plus BC squared. This is a theorem. You have proved this before, if you remember. So the theorem looks like this. For every something, if something happens, then something happens. This is an example of a theorem of this form. Many theorems are like this. So what is a direct proof? So a direct proof assumes the given assumption. So the assumption means this thing, assumption, p of x1 dot 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 xn, and uses the axioms or theorems, existing theorems, to derive the conclusion, which is q x1 dot dot dot. So you just assume the assumption, and you just use axioms or theorems, and then finally you conclude that, yeah, the conclusion is true. This kind of argument is called a direct proof. Yeah, so many proofs are direct, but there are also indirect proofs. You will see. Okay, so let me give you an example of a direct proof. But before doing that, let's define one thing, which is quite obvious. Everyone knows, or maybe not. Maybe you don't know this definition. Do you know the definition of an even integer? Do you think you know that? Is 0 an even integer or not? If you're not sure, you don't know the definition, right? So let me define this for you. Integer n is called even if there exists an integer k such that n equals 2 times k. This is the definition of an even integer. Similarly, an integer, so it's n is called odd if there exists integer k. Let's write this way. So this means k such that n equals 2k plus 1. This is the definition of an even integer and an odd integer. Now, let me ask you this question. Is 0 an even integer? Yes, according to this definition. So why is this why is 0 an even integer? Why? So this is a theorem. 0 is an even integer. This is a theorem. Proof. How can you prove this? K is 0, yeah. 2 times 0. 0 equals 2 times 0, right? And 0 is an integer. So it satisfies this condition. So yeah, it's an even integer. 0 is an even integer. So this is a theorem actually, but no one calls this a theorem because it's too simple. But still a theorem. And what about minus 1? Is this even integer or odd integer? Odd. Why? Why is this odd? K equals minus 1, yes. So minus 1 times 2 plus 1. You can write this as 2 times an integer plus 1. So it satisfies this condition, so this is odd. So for any integer, you can determine whether it's odd or even in this way, just using the definition. So if you say, oh, minus 1 is an odd integer because minus 1 equals minus 1 times 1 and 1 is odd, so it's odd. This is not a proof of this. It's kind of, you use extra thing. So if you only want to prove this using only this definition, you have to prove this way. But of course, if you know many theorems, then you can use other theorems to prove that minus 1 is an integer like I did. But for now, this is a direct proof that 0 is an even integer, minus 1 is an even odd integer, something like that. All right, now let me give you an example of a theorem, which is very, very well known. All of you know. So no one calls this a theorem for integers, but we are looking at examples of a theorem. M and N. If M is odd and N is even, then M plus N is odd. So this is a theorem, meaning we can prove this using definition and axioms or existing theorem. Can you prove this? Proof. Direct proof. We can give a direct proof of this. Yeah, of course we know that this is true, but we want to prove this precisely in mathematical language. So how can we start? Obvious? Just obvious? Yeah, it is obvious, but not for us. Because of this assumption, what can we say? Since M is odd, by definition, there exists, we can say there is K such that M equals 2K plus 1. Is that right? And since N is even, there exists, so we can say just for shorthand, we can say there exists L in Z integer, N equals 2L, because N is even. Now we want to show that M plus N is odd. So let's replace this with this thing. So we know that M is 2K plus 1, and N is 2L. So if you add these two together, you can factor these two, K plus L plus 1, right? But now what is K plus 1? Is an integer. So we expressed M plus N as 2 times an integer plus 1. So that means M plus 1 is odd. So this is the end of the proof. So usually in a math textbook, at the end of the proof, it's common to write this box or that box, field box, or this, or sometimes QED. So yeah, this means proof is finished, something like that. Any question? So this should be proved like this if you want to be very, very precise. And of course, this is not the only proof. In a theorem, for a theorem, there can be many different proofs. For instance, for the Pythagorean theorem, there are more than 200 known proofs, and could be more. So there can be many, many different proofs. And we will see two different proofs of this theorem. For example, there can be more than one proof to a theorem. Theorem can have one or two, but one proof is enough to say that the theorem is correct. You don't have to find more proofs to establish the truth of a theorem. As long as you have one valid, correct proof, that's a theorem. So the statement that we want to show is this: for all set x and y, x union y minus x equals y union. They're the same, but x union y. Let's prove this statement. For all set x and y, we have this equality. So proof. I'm going to give two proofs, so let's write proof 1. Oh, by the way, this is an example of a direct proof. We prove this just directly using assumption and axioms or things like that. Alright, so we want to show this. We need to show two things. We need to show two things. One. So if you want to show that two sets are equal, you can show this way. This is a subset of this, and this is also a subset of the other one. X union y minus x is a subset of x union y. Second, the other way around. So we are going to show two things. If you show these two, then we know that they are the same. Actually, that is also a theorem if you want. So let's prove these two things. First, I'm going to show this thing. In order to show that A is a subset of B, we can do like this. For every element in A, that is also an element in B. That is the definition of a subset. So let's consider an element in this set. And if you can show that X is also in this, then the first statement is established. Because we take this we take any X. So for any X in this set, if this is also in this set, then the first condition will be satisfied. Then what does this mean? X is in a union of two sets. That means either X is in the first set or X is in the second set. That's the definition of a union. Now let's consider two things. If X is in X, what can you say? So what is our goal? Our goal is to show that X is in this set, right? X is in X. Is it in X union Y? Yes. Then X is in union Y. This is just a definition of a, follows from the definition of a union. Just right. Now this is done. What about this? If X is in Y minus X, what can you say? Then is X in Y? It must be in Y because it is in Y minus X. X is in Y. Then what? X is in Y. Of course, it is in X union Y. This is a bigger set than this, so that's it. So this is, so we proved the first one. So the first one is done. For every element X in this set, we showed that it is always here. So this one is done. The second, let's consider one element from here. Now we want to show that it is also here. Then what? Similarly, X is in X or X is in Y. Right? Of course, yeah, that's. Now suppose X is in the capital X. Then what? What can you say? Can you say that it is also in this set? Yes. Because it's a union of X of something. You know, you don't need to look at this. It is already here. So this is okay. Now, okay, this is done. But we will slightly change this. Now, either X is in capital X or not, right? There are two possibilities. So if this is not, now if X is not in, suppose that X is not in Y, then what? Because we have either this or this is not the case. X must be here. Then X must be in Y. X is in Y but not in X. That means X is in Y minus X. Right? So it is in this set. That means X is in X union Y minus X. So we have proved the second thing as well. By the first and the second statement, which are proven to be true, we are done. So this is the end of the proof. This is one proof. Question? And we just use the definitions of these operations on set and the definition of a subset, definition of the equality of two sets, things like that. This is one proof. I'm going to give you another proof of this in the next page. So let me state the theorem again. X union Y. So proof, second proof. We can use existing theorems. So X union Y minus X. So we know that this can be, this difference of two sets can be written in this way. Y intersect X complement. This is, you know, we used this fact. Right? And here we can use the distribution law. X union Y intersect X union X bar. Here we use distributive law. Okay. And what is this? Here we assume that we have the universe set which contains both X and Y. So we say that both are subsets of U. So this is intersect, just the universe set, right? X union complement of X is the, this is called complement law. And finally, something union the universe is this thing. This is identity law. So we started from the left-hand side, and then by applying several theorems, we end up getting the right-hand side. So they are the same. This is the proof. So this is another proof of the same statement. Any question? Okay. So you can choose whatever method you prefer. So these are direct proofs. So let me tell you how to disprove a statement. Disproving a statement. We can also disprove a statement. In order to prove or disprove a statement like this for all x, p of x, disprove a statement means we show that this statement is false. This is what we say, what I mean by disproving a statement. So so you suppose that this is false and you want to show that this is false. Then we need to find x such that p of x is false. If you can find such an example x, then this disproves this statement. One example is enough. Such an example x is called a counterexample. Counterexample to this statement. So if you have a counterexample that is enough to disprove the statement. Just one example is enough. So example, for all n z plus, this means for all positive integers 2 to the n plus 1 is prime. So this is a statement of this form. For all x, p of x. For all n in positive integer, 2 to the n plus 1 is prime. Is this true or not? Okay, let's plug in n equals 1. If n equals 1, what is this? 3. This okay? N equals 2, 5. Okay. N equals 3, 2 to the 3 plus 1. 8 plus 1, 9. This is not a prime. So this is a counterexample. 9 is not a prime number, so n equals 3 is a counterexample. So this is it. This proves that this is this statement, meaning it proves that this statement is false. So the statement is false. So once you have a counterexample, you can immediately conclude that the statement is false. You don't have to look at bigger numbers. This one example is enough because it said for all n it is true. All right, prove or disprove. and C, A union B union C equals A intersect B union C. So you may have a problem like this. Prove or disprove this given statement. So you don't know yet whether this statement is true or not. If this is true, you will give a proof of this. Otherwise, you will disprove this by showing a counterexample. So I'm going to give you 2 minutes to solve this problem. Okay? 2 minutes. False? True? False. Okay, if you think this is false, can you tell me counterexample? A, B, C. If you think this is false, tell me what these are. There can be many, many different counterexamples, but try to find the simplest counterexample. Okay, I'm going to tell you. Let's say just this. You can have different counterexamples, that's fine, as long as it's really a counterexample. Okay, let's compute left-hand side. What is this? This part. Empty, intersect empty, union 1. So this is empty, right? This is 1. So left-hand side, let's say left-hand side is 1. What is right-hand side? This is empty, empty, and 1. This is 1. I mean this. Empty union 1. Empty. They are different. So in this case, because they are not the same, this statement is false. So this is false. So this is a counterexample. One counterexample is enough. You can find a different one, that's fine. Yeah. If you think you proved this to be true, then there must be some mistake in your proof.